Welcome, everybody. This is tinyML Talk. I am Carl Fieser. This is the first time I've done this one, so hey, everybody. I want to take a moment and thank all of our sponsors. And we have ARM, who's a strategic partner, DeepLight, Edge Impulse, Maxim Integrated, Qeexo, Reality AI, and SynSense. The next tinyML talk is going to be Tuesday, December 22nd, and that's going to be John Edwards, and he will be talking about low MIPS and memory machine learning for industrial vibration monitoring solution, aka not all AI applications are cat versus dogs on Facebook. I'd like to introduce Weiwen Jiang from the University of Notre Dame, and he will be talking about using AI to solve energy efficient AI accelerators for the edge. Weiwen Jiang is a postdoctoral associate at the University of Notre Dame. His research directions include co-design machine learning and quantum computing, including the first co-design framework, Quantum Flow, supporting and support from IBM Q networks, co-design of neural networks and hardware accelerators, FPGA, ASICS, SIMs, etc. He got the best paper nominations in DAC 2019, CODES, ISSS 2019, and ASP DAC 2020. Funding support from NSF, Edge Cortex Inc., and Facebook. Co-design of general applications and embedded systems, which got the best paper award in ICCD 2017. And with that, I will leave it to you, Weiwen.
Sure. Great. Thanks for the great introduction, and also it's a great time for us to connect the what Ian's output and how can we deploy the neural network onto the edge stuff. And so I'm very glad to be here to present my series of works on the AI democratization. The concept of AI democratization was proposed by Google in 2017. It aims to enable everyone to use artificial intelligence for their own application. To enable this, the core concept is the automation of AI system design, and the key technique is to use AI method to design the AI accelerators and AI systems, which is also known as automated machine learning. Today, I will report my research works throughout this year to promote the AI democratization. These works are conducted when I was in Professor Jintong Hu's group at the University of Pittsburgh, and also in Professor Yu's group at the University of Notre Dame. These works are collaborated with Sakia from Edge Cortex, and in these works, we developed the automatic co-design frameworks to simultaneously design both network and hardware. As we all know, in the past decades, the computing hardware has been widely deployed in every corner in our daily life, such as agriculture, military, power system, and so on. The computing hardware has greatly improved the efficiency of our daily life. Today, we expect that this computing can not only do this job repeatedly, but also do this job smartly. That is, we would like to integrate the intelligence into these systems. As stated in the beginning of the presentation, we are now entering the AI democratization era. Intelligence is going to different computing scales, such as the large-scale cloud computing, the middle-scale edge computing, and the small-scale sensor networks. Different scales have totally different requirements. For instance, the cloud computing requires the highest accuracy. Many edge devices require the real-time performance, and the sensor networks or the tiny AI require the extremely low power, as demonstrated in this slide. As a reform, AI solution can work for all scales. And let's narrow down to one scale, taking the edge AI as an example, as demonstrated in this slide. Even for one scale, there are many different applications. And in addition, there are so many different types of computing resources to build up our today's computing systems, such as CPU, GPU, and FPGA, as demonstrated in these slides. With the uniform real-time requirement, each hardware further needs a specific AI solution. So after the concept of AI democratization was proposed, we have witnessed the growth of this research field in the past 3 years. It gradually becomes clear that the AI democratization can be achieved through 2 levels of optimization. The first level is automation of neural network design. It can automatically identify a neural network according to the user application. However, only have the neural network is not enough, since the model needs to be finally deployed to the hardware for the execution. Therefore, it has a requirement of the second level of optimization, that is the automation of AI system design. When it comes to hardware, there are a lot of constraints like the latency, energy, privacy, and so on. My research works takes this constraint into consideration, and I focus on paving the road for the system design from the computing to the edge computing and the tiny devices. Now I will show the importance of the second level of optimization. As demonstrated in this slide, the intelligence is widely required in different computing platforms, such as the cloud computing, mobile phones, and customized hardware accelerators. Different computing platforms have different requirements. For instance, the cloud computing have the enough computing resources, and the objective is to maximize accuracy. For mobile phones, it has fixed hardware, and a trade-off between accuracy and latency need to be made. For the customized hardware, it further has hardware design flexibilities, and it is expected to achieve better trade-offs among accuracy, timing performance, and energy efficiency. As a result, no uniform network can work for all computing platforms, and exists a lot of works have developed different neural networks for different platforms, as demonstrated in these slides. To better understand the following topics, now let me introduce the fundamental problem for the automation of AI system. And showing these slides, we are given the data set, for example, the ImageNet dataset, a specific hardware like the mobile phone or FPGA, and a search space of neural networks where each circle in the shape represents one potential neural network. We need to identify a neural network in such a space, and the objective is that we are going to maximize both the software and hardware efficiency to achieve high performance. Before moving on, this slide gives us the outline of this talk. I will divide it into three parts. The first part, I will introduce the existing road for the automated machine learning from cloud computing to edge computing. Then I will introduce the potential two paths to achieve tiny machine learning. And finally, I will introduce our works towards the tiny machine learning on one specific path, that is on the customized computing path. The result is studied from the manual design of neural networks. At this stage, the development of neural network is quite expensive. Taking the evolution of network design for ImageNet as an example, it takes a large amount of time and involves a lot of experts with computer vision expertise to design the neural network. With such a large cost, and shown in this slide, it almost takes 1 year to evolve one architecture from another with higher accuracy. To overcome this, in 2016, Google proposed the new architecture search framework. It builds a highway to identify the neural network for the cloud computing. The automation is based on a search loop as demonstrated in this place. It is composed of two components. One is a controller, and the other one is a trainer. The controller will first predict a neural network, which will be sent to the trainer to be trained from scratch and obtain its accuracy. Then the accuracy will be fed back to the controller to update the parameters in the controller. After this update, it is expected that we can predict a better neural network for the next iteration. There are two limitations of the initial network. First, the search process is very inefficient. It will take hundreds, even thousands of GPU hours to complete the search process. Second, it has a mono objective on the accuracy, which may result in the identified network to be too complicated and only work for the cloud computing with enough computing resources. In response to the first limitation, the differentiable new architecture search, also known as DATS, was proposed in 2018. Ideally, they create a supernet, and the hyperparameter for the architecture and the parameter for the neural network can be trained together. As a result, we can only train the supernet once for the whole search process. Compared with reinforcement learning that need to train the neural network so many times, it can greatly improve the efficiency. So in response to the second limitation in 2018, the hardware-aware new architecture search was proposed. The first framework is ASICNAS, which is also proposed by Google. And ASICNAS adds the performance predictor module in the search loop as demonstrated in this place. After the neural network is predicted, in addition to be trained from scratch to obtain accuracy, it will also go through the performance predictor path to obtain the latency. Then the accuracy and the latency will be together to be feedback to the controller to update the controller. To improve the efficiency, and in the late of that year, ASICNAS and FBNet was proposed, and they are based on the differentiable approach as demonstrated in the previous slides. So to further pursue the hardware efficiency, the customized hardware is considered to implement the neural networks. The hardware accelerator design opens a new design space in addition to the original new architecture search space. However, there is a missing link between these two design spaces. More specifically, before our work, these two design spaces are explored independently, but we observe that they are coupled with each other. That means the base neural network is based on the hardware design. To close this gap, we proposed the first co-design framework, FNAS, in 2019. And FNAS can simultaneously explore both space in an integrated search loop. This work obtained the best paper nomination index that year. Recently, the differentiable approach is also applied for the co-design framework, for example, the EDDNet from UIUC. Now we have seen the road from the cloud computing to the edge computing using either mobile phones or FPGAs. Moving forward, we are going to see how the path is to evolve towards the tiny machine learning, that is for the tiny devices. Followed by the mobile phones, the first path, also the typical considered path in the current stage is to apply the hardware-aware neural architecture search to microcontroller. The property of this path is that the computing resources are for the general purpose, like the CPU and GPU. On the other hand, the FPGA represented customized computing further evolves to application-specific integrated circuit that is also known as ASIC. With the hardware configurability, we need to co-design for such kind of computing platform. Interesting, I found that recently such a co-design philosophy is also applied to the NAS for the microcontroller, because we need to not only have a predictor to predict the latency, we also need to design the compiler stuff so that the philosophy has already been applied for other places. This slide demonstrates the typical research works for all computing platforms. And we can see that Google leads the AutoML for the cloud and the mobile phones, while our works lead to the co-design framework for the FPGA and the ASICs. And in the following, I will present our work on the ASICNAS, which is collaborated with Facebook and Georgia Tech. So far, do you have any question at this moment? If you have any question, we can stop a little bit at this position, I think.
No questions so far. Did you, I had one. So there was the co-design for skipping in terms of NAS for tinyML devices. You just found out, you haven't done any research specifically on this yet?
So the question is about the
sorry, NAS design for microarchitectures based on your previous slide.
Yeah. Actually, our approach is not for the microcontroller, but we focus on the ASICS devices. I mean, it's for the ASICs, because I will show the motivation why we focus on the ASIC, not the microcontroller, in the following slides.
Got it. Yeah, I don't think there are any other questions right now.
Sure. Thanks for the question. So I will continue to introduce our co-design framework using the ASIC as the example. So in this year, we have proposed the exploration framework for the neural networks on the ASIC chips. And our ASP Dank work obtained the best paper nomination, and our work on the on Dank also obtained the Facebook Research Award. And so when it comes to the ASIC, the first question is why we focus on the ASIC, not the microcontroller, as Carol just asked. So as reported by Tratica, ASIC are becoming more popular for the implementation of AI application than FPGA, GPU, and CPU. And it will gradually dominate the market. This is because that the ASIC has the natural advantages in the energy efficiency, latency, and error stuff. However, the design space of ASIC is really huge. When designing an ASIC platform, we need to determine the data flow, the resource allocation, the topology, and the communication. Furthermore, there are distinct sub-design specifications like the utilization of processing elements, the memory allocation, the communication mechanisms. All these factors lead to a complicated and huge design space. Specifically, as demonstrated in the slides, the existing ASIC accelerators are based on distinct data flows. For instance, the DLA proposed by the NVIDIA is based on the weight stationary data flow, whereas Steno is based on the output stationary data flow. So we currently have a lot of excellent ASIC designs, and therefore there is no need to design the ASIC accelerator from scratch. Instead, this ASIC accelerator design can be templated in terms of the different data flows. Then we can build a pool of ASIC templates and select a dedicated template for a given application in the design phase. So after we build the templates pool, there is a new question arises, whether one template can fit for all neural network architectures. The answer is no. In this slide, we demonstrate that in terms of the resource utilization, different data flow are suitable for different neural operations. For instance, the DLA is more suitable for the operation with low resolution but deep channels, but still not is more suitable for the high resolution and shallow channels. Therefore, the problem is defined in the slides, and in this year, we are the first to propose the co-exploration of new architecture and heterogeneous ASIC accelerators. The problem is described here. We are given multiple machine learning tasks and a pool of ASIC templates. With the constraint, we were also given the constraint on the latency, power, and error. And we are going to determine the new architecture for each task via the new architecture search approach. Then a specific new architecture, a dedicated template will be selected from the template pool, and the resource including the number of processing elements and the bandwidth will be allocated to each template to finalize the heterogeneous ASIC chip. After this, the mapping and the scheduling will be conducted on the ASIC chip. Finally, we can obtain a heterogeneous ASIC chip to support multiple tasks as demonstrated here. For example, we use image classification and image segmentation as different multiple tasks in our inputs. To solve such a problem, we propose ASICNAS Framework. It contains 3 main components, including the co-exploration controller as demonstrated in this place. It will explore the hyperparameters of multiple DNNs and also the heterogeneous ASICs parameter like the bandwidth and the number of processing elements. We also integrate the optimizer selectors, which will help us to speed up the search process. Finally, we also integrate the evaluator to obtain the accuracy and a penalty in terms of the design specifications. So dive into details for the controller. We based on the reinforcement learning approach and use a recurrent neural network to simultaneously predict the multiple neural network architectures. And also we integrate the accelerator design parameters into the controller to realize the co-exploration of neural architecture and hardware design. For the optimization selector in different search phases, it will apply different optimization goals to accelerate the convergence process. Finally, for the evaluator, it also contains 2 passes. First, for an identified neural network, it will be trained and validated on a head-out dataset to obtain the accuracy. On the other pass, the custom model is used to obtain the hardware matrix of the neural network layer on different ASIC sub-accelerators. Based on this information, actually we provide an automatic algorithm, a mapping algorithm to and also it contains the scheduling to help us to develop the final full chip, and the goal is to achieve the lowest latency and power. So we conducted the experience on 3 different workloads under the design specifications, and the design specification here is demonstrated in the black diamond here. And from these results, we can observe that simply heuristic algorithm that is represented by the blue stuff here, and we can show that it cannot achieve a very high accuracy. And the ASICNAS can guarantee that all the explored solution to meet the design specification, which is presented by the green points, and the final result is represented by the red stars. And we can see that the identified solution can achieve very high accuracy. This table has further reported the comparison results of multiple data set workloads with other approaches, including the sequential NAS and the sequential conducting the optimization for NAS and the ASIC designs, and also the sequential NAS design and the hardware-aware new architecture search. And then we compared it with our co-design approach. We can observe here that the identified network by the sequential NAS and ASIC is too complicated so that it cannot be accommodated to the ASICs. Cannot be accommodated means that the design specification cannot be met. For example, the latency, as demonstrated in this place, the cross here, the latency, energy, and the error cannot be met, the requirements. While the hardware-aware-based design, the second approach from ASIC to the hardware awareness, this approach can help us to guarantee the latency and the hardware efficiency to be met, the requirement. However, it has the low accuracy and compared with this our stuffs. So finally, the proposed co-design can make the best trade-off between the accuracy and the hardware efficiency. Okay, so finally, I will introduce some future work and the concluding. So in the past year, we have also explored the computing in memory architecture to solve the memory bottlenecks. I think this is a well-known problem in the implementation of machine learning, the memory bottleneck. And we observe that the emerging devices like the computing memory, the RAM or the memory register can be useful to solve such a problem. However, there is also a lot of challenges like it has a device variations. And we propose the Notre-CIM framework, which is a cross-layer optimization framework, including the exploration of new architecture, the quantization, the data flow, the circuit design, and also the device selection. So that with such a framework, we are expected that we can find a more energy efficient solution for the machine learning application, which can be suitable for the tinyML era. And in this slide, in the following slides, two slides is I will conclude this talk. First, there are two paths for the auto machine learning evolved from the cloud machine learning to the tinyML. I know that many people think that the typical ways for the first pass from the GPU to mobile phone to microcontroller, but we are also emphasize that the second pass is also very important. That is for the customized computing using FPGA and ASIC. Second, we have paved the road for the second pass for the customized hardware. And due to the hardware design complexity, it is more difficult but worse to do so for the higher energy efficiency. In addition, the co-design is essential for such a path since you cannot expect the user to design the hardware by themselves, right? And so based on this, we proposed the automated framework, co-design framework to bridge such a gap. And finally, thank you for your attention. And I would like to answer a couple of questions from the audience. By the way, I'm currently on the job market for faculty position this year, and more information can be also found in my personal website by scanning this QR code. Thanks.
Thank you, Weiwen. That was a great presentation. Let's see. There's a few questions. Let's see. I'll pick one, and then I have a follow-on question for that one. So Joey asks, "Great work. Does this mean you combine the NAS and hardware design into the same search space?"
Yes, actually, as demonstrated in the second part, the last part, actually we use the integrated controller to integrate explore the hyperparameters for the new architecture, that is for the new the search for the neural network, and also we create the hyperparameters for the hardware design so that these two design space can be explored simultaneously.
My follow-on question then is, how are you optimizing for both concurrently? And you're using reinforcement learning, right?
Right. Actually, we use the reinforcement learning so that we not only consider for the feedback of the evaluator, we not only feedback the accuracy to update the hyperparameters in the controller, but we also consider the hardware efficiency like the power, the energy, I mean the power, latency, and also the error. And this metrics are obtained from the simulator, which one is based on the method proposed by Georgia Tech. So that based on this information, we can formulate a integrate a reward, and such a reward can be used to update the controller for a better solution.
Interesting. Cool. Another question from Kasaba. Algorithms and models are often updated, while ASICs are a bit more difficult to update because it's a piece of hardware in the field. Can you comment on how much your ASICs are specific to the model and how much they would work with it? They would work with a different model, or an updated model. So if you want to update your model after it's trained, what do you do then?
Okay, that is a really great question, and this question I think is much more related to the fundamental design of the ASICs. For example, the data flow that we use, and fundamentally, actually, you know that the unlike the traditional ASIC that is for the specific application, specific task. For now, actually, we have the so-called deep cores or the deep ASIC like the Google's TPU, so that the fundamental operations for the neural network are the same, so that the data flow can support different operations. And we use such a templates, we use such a ASIC design to accelerate the whole procedure. So that basically this question is related to the fundamental templates that we are going to adopt, and if it can support different kind of computation and different type of models, actually we can support different neural networks. I think this is the answer for this question. Thank you.
Got it. Yeah. And I think that answered Sergey's question as well. Let's see, because he asked, but in many ways, practical domains models tend to drift. How can one be sure that his ASIC is stable for such matters? I think that answered that. Okay. And then let's see, one more question from Christopher just came in. Weiwen, what are the main drawbacks to your co-design ASICNAS approach?
Okay, actually, I think this is also a very great question. You know, that for currently we are aiming to bridge the two design spaces for the hardware exploration and the software exploration, and we applied the traditional reinforcement learning approach so that the search efficiency is not as high as a differentiable approach. And another thing is that if we are going to want to extend for so many devices for so many applications, actually, I think this problem will be zoomed out so that we need to consider the search process, the efficiency of the search process. I regard this as a main problem that we are going to solve. Actually, we are also studying on this topic.
That's great. Are you planning then, is that going to be worked in a next paper or in your next, or you're going to try to address that with your next approach, or is that something you're acknowledging and saying you'll have to get to later?
Oh yeah, actually actually in this year we also provided other solutions for improve the efficiency of the AutoML. Actually, this one is not specific for the ASIC stuff, but it is the traditional problem for the auto machine learning. And we actually, if you are interested in, I think you can visit my website, and the one we propose is called HotNAS, and we are going to stand on the shoulders of the giants. That means that we are going to use the existing models to accelerate the search process. Yeah. So we are thinking about this, and also we are going to apply such approach to the ASIC stuff. The original one, the HotNAS, is based on the FPGA, but we are going to extend it to the different platforms.
Awesome. Great. I think that's a great place to wrap up. Thank you again, Weiwen. If anyone has any questions or has roles, since he's currently on looking for a new role, definitely reach out to him. His contact information is there. We thank our sponsors, ARM, who is great software and hardware foundation for tinyML, focusing on both software and hardware optimized for edge devices. Deep Light, we use AI to make other AI faster, smaller, and more power efficient. tinyML for all developers with Edge Impulse. Go ahead and get a free account at edgeimpulse.com. Maxim Integrated, the new Max 78000 implements AI inferences at over 100x lower energy than other embedded options. Now the edge can see and hear like never before. Qeexo AutoML for embedded AI, automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI is for building products. SynSense builds ultra-low power sub-milliwatt sensing and inference hardware for embedded mobile and edge devices. We design systems for real-time, always-on smart sensing for audio, vision, IMUs, biosignals, and more. Don't forget our next tinyML talk. It's going to be the last of the year. Tuesday, December 22nd, John Edwards, and he will be talking about low MIPS and memory machine learning industrial vibration monitoring solution, aka not all AI applications are cat versus dogs on Facebook. And that will be at 8 a.m. Pacific time. And thanks again, everyone.